Satellite internet through advanced satellite communications technologies has become an important part of our global telecommunications infrastructure. It can provide communications services to any place on Earth, including hard-to-reach, unserved, and underserved areas. I'm going to show you the fundamentals of modern satellite communications that help you describe the satellite applications and explain how the satellite internet works. I'm Ryan Hu, and I have been an engineer, researcher, and instructor in the telecommunications field for over 17 years. If you ever wonder how satellite internet and communications work, please come join me in my course on Satellite Internet and Communications Fundamentals. For people who live in urban areas, wired internet access is a given. But for communities in hard-to-reach places that lack infrastructure and for people in the aircrafts or ships and sea, alternative connectivity options are needed. That's where satellite internet comes into play. Satellite internet is a general name for internet connectivity provided by various satellite systems. Although each satellite system may not have the same design, they do share some common grounds in communications. Let's start with a minimalist scenario of using the internet. We have a laptop user attempting to access the multimedia service from a service provider connected to the internet. The missing part is the physical connection between these two ends. Satellite communication can bridge this gap, linking a user on the ground to a satellite in space and a satellite in space to the service provider on the ground again. These connection types have names. The downlink, where a satellite sends messages to the Earth, and the uplink, where messages are sent to the satellite. In a general scenario of a satellite network, where one link is between a satellite and a user, and the other link is between the satellite and the remote information server, there are two downlinks and two uplinks based on the direction of the message transfer. This setup can scale up to support multiple users. It can also enable one-way communication scenarios supporting information distribution or video broadcast. It can also enable two-way communication scenarios such as interactive applications and internet services. These connections usually use radio signals, so the radio receivers and the transmitters need to be available on both ends. On the service provider end, an Earth station with the radio transmitter needs to be available to send radio signals representing the multimedia content such as audio or video streams. On the user end, a receiver with a radio antenna also needs to be available. A connection from an Earth station to a user terminal is called a forward connection. The reverse connection is the return connection. The radio signals cannot be sent at a random frequency, but need to follow regulations. Some commonly used specific frequencies for satellite communications are C, Ka, and Ku frequency bands. C band ranges from 4 to 8 GHz. Ku band ranges from 12 to 18 GHz. And Ka band ranges from 26 to 40 GHz. And the Q or V band ranges from 40 to 75 GHz. At this point, we have almost everything we need to make the magic happen. There's one more thing we need to ensure. We need to make sure the satellite's signals cover the user for our internet connection, just like the GPS service relying on satellite coverage. Now, the user can enjoy multimedia streaming content from the laptop from the remote service provider with the satellite backhaul. Satellite communications are all around us, from Earth observation, scientific research, to tracking, navigation, and information services, including telephony, broadcasting, and internet. The Earth observation satellites are equipped with sensing instruments for various missions that provides essential information about ocean, ice, land environments, and the atmosphere. For example, satellite data has been used for air quality assessments through tracking smoke plumes and toxic gases, such as carbon monoxide and sulfur dioxide, as well as carbon dioxide. They can also help fight climate change through monitoring deforestation, rising sea levels, and greenhouse gas emissions in the atmosphere. Earth-observing satellites can perform geophysical measurements to understand earthquakes with a satellite radar. The wildfire can also be monitored through the visible infrared imaging radiometer suite sensor on the polar orbiting satellites. They can monitor the crop yields to assist agricultural activities and production. Satellites can also help with transport and logistics applications. For example, assets, cargo, and vehicles, including ships, cars, airplanes, can be optimally scheduled in a supply chain through satellite tracking and navigation capability, and through communications capability to transfer various data. These data include vehicular health, traffic, weather conditions, and positions. Without data to support worldwide logistics, food and other goods can spoil or create backlogs before they reach their destination via different hubs. Satellites have been broadly used in information services, such as multimedia broadcast and internet access to rural and remote areas, with no terrestrial infrastructure. With satellite connectivity, users can access enhanced multimedia streaming and various digital services and applications, including the first responders and the defense applications, as well as the Internet of Things, where numerous connected objects with sensors can transfer data around the world through the satellite network. Recent advancement in the satellites in hardware and constellations can provide broadband internet access to anywhere on Earth, where many services currently using the terrestrial networks. Satellite communications have enabled many tasks we cannot easily do on the ground and provide a key infrastructure in space for global information and communications services. One of the major driving forces of the satellite communications system is the large constellations of low Earth orbit or LEO satellites, as well as the high-throughput satellite capacity. With the advanced LEO satellites, enhanced broadband and low latency can enable various services. The integration of LEO satellites into 5G and beyond telecommunications networks is expected to be seen, where broadband, similes, and wide-scale coverage of internet services will be available across the globe. In this case, the business opportunities arising from the 5G and beyond connectivity still hold for the advanced satellite internet. Satellite systems require a large ecosystem to operate. Consumers need on-premise equipment, and the satellites must be launched into space. Each system relies on thousands of space and ground components. Existing sectors that will be positively impacted by 5G will benefit from this extended coverage, where additional customers can be reached. These sectors include manufacturing, healthcare, agriculture, transportation, smart cities, education, gaming, and augmented reality, where the services in these sectors can be delivered to global users in high quality. Also, satellite constellations and advanced satellite systems will enable new architectures for computing and communications services. These services include, for example, satellite-based cloud or edge computing, satellite-integrated network architectures, and satellite-assisted high-altitude platforms, such as unmanned aerial vehicles. The Internet of Things applications will benefit from the global coverage and capacity of the satellite systems. The connected objects deployed in any remote area can connect to the Internet for various tasks. Satellite networks can also enable other communications services, such as quantum communications or quantum key distribution for secure communications. All these create unprecedented changes to the businesses involved in not owning satellite suppliers and operators, but also a value creation chain. A generic satellite communications system has three segments: a space segment, a ground segment, and a control segment. A space segment consists of one or more satellites in space. Satellites in space can communicate with each other through the inter-satellite links. A satellite has a payload and onboard terminals. The payload is an onboard module using antennas for producing and transferring data with Earth stations. Inter-satellite links can be radio or optical links that can be used to transfer messages between the satellites in space. The ground segment consists of Earth or ground stations for handling the traffic with the satellites. These Earth stations include user stations, gateway stations, and service stations. Example user stations include portable satellite phones and very small aperture terminals called VSAT, where user terminals such as laptops and mobile devices are connected to. Gateway stations are connected to the terrestrial communications networks, such as the Internet. Service stations are for distributing and collecting information to and from user stations. The control segment usually consists of stations and facilities for tracking, telemetry, and command, and the network management as well. An example facility of a TT&C stations can be shown here. The main satellite services as categorized by the International Telecommunications Union Radio Communications Section, called ITUR, include fixed satellite service, FSS, mobile satellite service, MSS, and broadcasting satellite services, BSS, as well as other services. The FSS is a radio communications service between Earth stations at a given position, where one or more satellites are used. FSS supports all types of telecommunications and data network services, such as telephony, radio, TV, data, and Internet. The MSS is a radio communication service between mobile Earth stations and the satellites. MSS includes maritime, aeronautical, and land services. To support mobility, mobile Earth terminals are often small and handheld devices. The BSS is a radio communications service where satellites transmit or retransmit signals intended for direct reception by the public, including an individual or a community. BSS has been used for radio and TV broadcasting. Other satellite services include Earth observation, space operations of spacecraft, and amateur radio satellite service. And there are inter-satellite services for communications between satellites in the same or different orbits. These satellite services need to fit various network applications, ranging from messaging, telephony, audio or video streaming, to distributing information and multimedia internet service. A satellite needs to be launched to a curved path around an object in space, and this curved path is called an orbit. Just like the International Space Station, a satellite is put into one of the Earth orbits, circling around the Earth's surface at a certain distance. And such a distance a satellite circling around Earth's surface at is called altitude. There are a few popular orbits that satellites are launched in. First, geostationary orbit, GEO, circle the Earth at an altitude of around 35,700 kilometers. They are parked over the equator from west to east, traveling exactly at Earth's rotation rate. In other words, geosatellites appear to be stationary to a fixed location above Earth. GEO is a popular orbit of the geosynchronous orbit, GSO. Different from GEO satellites, GSO satellites can have orbits that are not exactly above the equator, and they can have elliptical orbits, where these orbital paths are said to have degrees of inclination. It also means the satellite's path will take it north and south of the Earth's equator during one complete orbit. Some satellites can also orbit around some synchronous orbit at an altitude of 600 to 800 kilometers to pass a location on Earth at the same time every day. Some satellites for Earth observation missions often use this orbit. Most satellites are launched into low Earth orbit, LEO. Satellites in a LEO circle the Earth at an altitude between around 160 to 2,000 kilometers. A LEO satellite does not need to take a specific path around Earth. A MEO satellite is closer to Earth and moves much faster than a LEO satellite. Each satellite takes 1.5 to 2 hours to complete a full orbit around the Earth. A large collection of satellites, called a satellite constellation, needs to be used for global coverage. A design of a LEO satellite constellation can be shown in this example, where 66 satellites are in its Iridian satellite constellation. Median Earth orbit can take a range anywhere between LEO and GEO. A MEO satellite also does not need to take a specific path around Earth, and is used by a variety of satellites for different applications, such as remote sensing and navigation. For example, GPS uses a 24-satellite constellation. Each satellite flies over at an altitude of around 20,000 kilometers. At any given moment, every point on Earth has access to 4 GPS satellites. The area of the Earth visible to the satellite is called footprint. It's generally dependent on the satellite's orbit and the beam pattern of the satellites. A beam is a radio frequency signal sent by an antenna with the satellite payload to cover a limited geographic area on Earth. A beam pattern can be determined by the spot beams. At this point, we can roughly illustrate the footprint comparison between LEO, MEO, and GEO satellites here. Satellites are designed to launch in an orbit over a certain altitude and operate standalone or with other satellites in a constellation, providing communications services for various users and applications on the ground. GEO satellites have been used to provide weather monitoring and other Earth observing services, satellite radio, as well as various information services. A well-known example is the Intelsat communications satellites providing international broadcast services. The popular VSAT satellite networks typically use GEO satellites as well. VSATs can be used for voice, data, or video transmissions, for marine, mobile, and fixed satellite internet service. GEO satellites can cover a large area of Earth, meaning only a few GEO satellites can provide global coverage. As an example, the footprint of an operational GEO satellite can be shown here, where the outline shows the satellite coverage. Let's take a look at the VSAT system setup as an example. The VSAT system includes the Central Earth Station, often referred to as a hub station, and various VSAT terminals as user stations, and the TT&C station, where it is not shown here. With these stations, a VSAT network can support a typical connection for internet access, and it can also support additional topologies for various communications needs. For example, 2 VSATs can connect to each other through the point-to-point topology, VSATs can also form a star topology, where VSATs are connected through a hub station connected to the satellite. VSATs can also form a mesh topology without a central hub, and they can connect to each other through the satellite. Such setup can also be useful for the digital TV broadcast and internet access based on other standards, such as the Digital Video Broadcasting Satellite DVB-S2 and its extension DVB-S2X, and the Digital Video Broadcasting Return Channel via Satellite 2 called DVB-RCS2. The geosatellite systems have provided typical setups, which can support a variety of useful applications, such as satellite radio, TV, data, and multimedia internet services. A MEO satellite system has different orbits and system components than geosatellites. The well-known GPS and Galileo navigation systems are examples of MEO satellite systems. MEO satellite systems have been used for communications across space, air, land, and sea. However, since a MEO satellite orbits at a lower altitude than that of a geosatellite, it needs a constellation to cover a large Earth surface. Due to the movement pattern, MEO satellites will not constantly stay over the same surface area. It will need another satellite in its constellation to hand over the traffic between them to maintain the service to that area. A real-world example of MEO satellite constellations can be seen in the GPS and Galileo systems. In the Galileo constellation, there are 30 MEO satellites, including 3 active spares, orbiting in 3 equally distributed orbital planes. They are at an altitude of 23,222 kilometers. In the GPS constellation, we can see there are 24 MEO satellites in 6 equally spaced orbital planes. They are at an altitude of around 20,200 kilometers. Since MEO satellites orbit at a lower altitude, communications has less latency than that of LEO satellites. The signal travels a shorter distance between satellite and a ground station. The estimated round-trip time can be reduced from several hundred milliseconds to around 100 milliseconds, equivalent to some terrestrial networks. It's also possible to provide higher bandwidth than GEO. The latest MEO satellite system, such as the new SES-03B satellites, have claimed to provide a throughput performance of multi-gigabit per second. Earth stations would use tracking antennas due to the motion of satellites. The antennas to be used can be based on a mechanical mechanism, whose beams can be mechanically steered, or they can be based on a phased array whose beams can be electronically steered. A MEO satellite system can be used for broadband internet service. Its components have some differences from a GEO satellite system. LEO satellite systems have provided essential communications services such as voice communication service from the Iridian LEO satellites started operation in 1998. LEO satellite systems orbit at a lower altitude and a higher speed than MEO and GEO. Due to the constant motion of satellite, one LEO satellite can only cover a region of the Earth in 30 minutes or less. The coverage area of the region is dependent on different factors, such as inclination, altitude, elevation, and the radio link parameters. For example, we can estimate a radius of 580 kilometers for a LEO satellite coverage at an altitude of 550 kilometers with an elevation of 40 degrees. To cover a large area on Earth, LEO satellites usually operate in a large constellation with hundreds or thousands of satellites, called mega constellation. The large constellation may pose concerns for space debris. Some LEO satellites have considered using onboard propulsion systems to intentionally deorbit the satellites, making them burn up in Earth's atmosphere. There are other characteristics of the LEO satellite network that make it a promising internet connectivity option. Because LEO satellites are close to the Earth, they can be small and require less power. Smaller LEO satellites have less costs to design, manufacture, and launch. The low latency and increased throughput are other reasons for their popularity. The latency and the throughput are two key performance metrics for data communications. Lowering the latency and improving the throughput can enable applications to transfer a large amount of data in real time. Example applications include video conferencing, video calls, and gaming. In addition, the large constellation and constant mobility of satellites can possibly reduce the blockage of signals or jamming attacks. The redundancy design in a satellite constellation can further improve the secure and reliable communications services. Compared to the MEO and GEO satellites, LEO satellites are closer to the Earth's surface. This enables LEO satellite-enabled internet service to achieve its cleaned performance equivalent to fiber optical cables. A LEO satellite network still has the stations in space, ground, and control segments, similar to those in a GEO satellite system. However, the size of a LEO satellite constellation may vary, ranging from a few hundreds to tens of thousands satellites. For example, from the proposed launch plans so far by the industry players, SpaceX's Starlink aims to launch around 42,000 satellites. Amazon Kuiper plans to launch 3,236 LEO satellites. Telesat plans to initially launch 298 LEO satellites. And OneWeb intends to launch around 650 LEO satellites. A real-world example of the large LEO satellite constellation can be seen from the Starlink project, where hundreds of satellites launched to different LEO orbital planes can be seen. The gateway stations are usually at fixed locations. A LEO satellite network consists of gateway stations deployed in possibly more density than those in a MEO satellite system. These stations need to deal with the handovers of satellite signals, which doesn't usually occur in a GEO satellite network. The required number of the gateway stations varies. It needs to be determined based on, for example, constellation, designs, economic, and system capacity factors. The deployment of the gateway may also depend on the application's specific requirements. For example, a gateway station can be installed at a data center to connect it to the LEO satellites. This can reduce the latency from a regular gateway station to a data center, where most cloud services are offered to consumers and enterprises. As an example, let's see the proposed deployment of ground stations that can be seen in a third-party tool, where ground stations are labeled as orange dots, which are distributed across the US to support the regional LEO satellite traffic. One way of reducing the use of gateway stations is to transmit the data using the inter-satellite links. Data messages get forwarded right in space instead of going through gateway stations each time. Such inter-satellite links can be radio or optical. Due to the complexity of large satellite constellations, various links and limited resources, routes and satellite operations need to be designed for optimal performance. The user station in a LEO satellite internet aims to be miniaturized combined with user terminals. For example, a small satellite dish and a Wi-Fi router are used as the Starlink user terminal to access the satellite internet service from the user's end. The The satellite dish is used to connect to their LEO satellites, and the app can guide the user to set up the antenna in an optimal position. The satellite dish is also motorized to tilt the elevation with a phased array antenna. The Amazon Kuiper project also plans to use a phased array antenna with 12-inch or 30 centimeters diameter as part of their user terminal, which can support up to 400 megabits per second throughput on the user end. The kits you just saw aim to give you an idea of how the user terminal look like, but they may become obsolete down the road. Now we have seen the architectural components that make a LEO satellite internet. These internet service can potentially serve any place on Earth with low latency broadband performance. The latest LEO satellite constellations can provide ever-enhanced broadband satellite internet access with broad coverage on Earth. As a result of technological innovation, a single user can enjoy enhanced broadband with low latency from a satellite internet service. The high-throughput satellites can also handle data traffic from tens to hundreds of gigabits per second, supporting many broadband services. Such capability can rely on some enabling factors, such as spectrum bands, inter-satellite communications, traffic routing schemes, and ground stations. Satellites have primarily used the C and Ku bands where possible congestion with existing satellite services, such as TV broadcasting, can degrade the bandwidth provided by satellite internet. To avoid such congestion, new LEO satellite operators have moved to use the Ka band and Q or V bands at extremely high frequency to support enhanced throughput. However, these bands are more susceptible to weather conditions than C and Ku bands, so a multi-antenna system can be used to allow new LEO satellites to benefit from all spectrum bands. The geographically deployed ground stations for LEO satellites also play a key role in supporting the broadband traffic between end users and application service providers, such as video, streaming services, or cloud computing. In addition, the traffic routing between satellites through inter-satellite links is also important. Using a well-designed routing mechanism can reduce the need for ground stations, so the actual number of ground segments for a broadband satellite internet may be variable and dependent on the ongoing user requirements and market demands. Satellite communications have been used in previous generations of mobile telecommunications technologies, such as 2G, 3G, and 4G. Back in the 1990s, 2G systems such as GSM were used for digital telephony applications. They were supported by several satellite communications providers such as Iridium, Inmarsat, and Globalstar. With the deployment of 3G systems around 2000, new satellite communications emerged to provide not only telephony service but also multimedia applications. Example satellite systems include the Inmarsat Broadband Global Area Network, BGAM, which can support 144 kilobits per second and a higher bandwidth for multimedia data transmissions. Satellite radio systems such as Sirius Satellite Radio and XM Satellite Radio, which later became Sirius XM Radio, can support high-quality audio signals. Satellite TV systems also emerged around that time to support digital video signals. The integration of satellite network components into 3G and 4G has been made in the standardization efforts. The 3G technology, UMTS, also specifies the satellite UMTS systems, allowing satellites to provide direct access to UMTS networks. Compared to 3G, 4G systems require the support for higher bandwidth and mobility. And in the 4G standards, IMT Advanced Two application scenarios are mentioned for satellite communications in 4G. They are two-way communication scenario and interactive digital multimedia broadcasting scenario. In these scenarios, satellite interfaces are expected to be compatible and have a high commonality with the terrestrial network interface. With the upgraded capacity of LEO satellite systems, solutions for LTE satellite networks have been made possible. Recent technological advancement allows seamless integration between satellite components with terrestrial components in 4G. For example, Lockheed Martin provided LTE over satellite solutions in 2019. Also, in 2020, Blue Walker LEO satellites enabled the orbiting cell towers to provide 4G service to users directly from space. This storied history is the foundation of satellite internet communications. 5G has been standardized to achieve three key usage scenarios: enhanced mobile broadband, ultra-reliable low-latency communications, and massive machine-type communications. The first usage scenario includes the support for multi-gigabit per second throughput for applications with extensive data traffic growth, such as virtual reality. This scenario can be supported by the modem MEO and the LEO satellites. The second usage scenario includes the support for applications requiring very low latency and high availability and reliability, such as mission or safety critical applications. Satellites can facilitate such a scenario through the caching or distribution of contents, although the latency as low as a few milliseconds is challenging to achieve for satellite ground links. The third usage scenario supports the massive number of Internet of Things connections with low battery life and wide coverage. Satellites can support narrowband and broadband connectivity for IoT devices and provide wide coverage in hard-to-reach and unserved areas. In terrestrial networks, 5G has already been deployed in many major metropolitan areas. A typical terrestrial 5G network starts with the user equipment like a mobile device which connects to the 5G base station. The 5G base station, called G Node B, will connect to the 5G core network, which can interface with external communications networks with application service providers. We can simply label these links to A, B, and C. The 5G Standardization Organization, 3GPP, has considered integrating satellite communications into the terrestrial 5G telecommunications networks, where different integration options are proposed. The first option is to let the satellite communications be a backhaul for link C. In this case, the satellite network can be viewed as part of an external network to the 5G network on the ground. The second option is to let the satellite communications offload the 5G traffic, where link A and the 5G base station will be replaced with the satellite network setup. A user can still access data contents from application service providers through the 5G core network with help from a satellite network. The third option is to consider satellite communications as part of the 5G network. Satellite networks will be part of the distribution of 5G traffic. In this case, the satellite network will provide link A and the 5G base station is capped. As an element of the 5G network, the satellite link needs to meet some requirements. For example, the considerations of latency and the continuation of link connectivity with MEO and LEO satellite constellations need to be made, as we know that the satellites in these considerations are constantly moving. A 5G system, if integrated with satellite systems, can provide seamless global coverage with promising performance. The sixth generation of telecommunications, or 6G, is expected to provide better speed, intelligence, flexibility, and coverage than 5G. To make this possible, standardization groups are considering the use of new enabling technologies, such as terahertz-based wireless communications, AI-enabled communication technologies, the non-terrestrial networks for 6G, and the flexibility of interacting vehicular networks on the ground, satellite networks in space, and aerial vehicles in the air. Satellite networks will be an important part of 6G. LEO satellite launch plans from major industry players are expected to happen in the next several years. This timeline supports the development of 6G by 2030. The goal ITUT, a United Nations authority for telecommunications system standards, has set. Also, the advanced satellite networks, which give the great promises of having fiber optical network equivalent performance, can be used to provide backhaul links to the future networks and function as the connectivity option to support flexible scenarios. For example, the LEO satellite networks in 6G may also be integrated with unmanned aerial vehicles and vehicular networks to provide flexible connectivity to any area on Earth. Such LEO satellite networks in 6G may also support a broad spectrum of applications, including virtual education, healthcare, sensory virtual reality, and holographic conferencing. However, the use of large LEO satellite constellations is still in its early phase. The challenges may come from the market success from the satellite internet operators and the advancement of the technologies that can meet tomorrow's needs. LEO satellite communications is also expected to keep evolving to better support 6G networks from hardware and software modules to resource orchestration and operations automation. As new fleets of LEO satellites are launched in space in the next 5 to 10 years, they will become an increasingly important part of the global telecommunications infrastructure. Now it comes to an end of this course. As the satellite technologies keep advancing, as a next step, you can do the following to learn more about the satellite internet and communications. Read recent satellite studies and discussions through International Telecommunications Union, related publications, and the standards development organizations. Check some real-world examples or setups of satellite communications systems based on the types of satellite communications services and the satellite communications providers, such as the ones mentioned in the course. Extend your understanding of the key applications that can be enhanced through the satellite connectivity, such as the massive machine-type communications driven by the Internet of Things technologies. Thanks for watching my course.